Okay, this is a lesson on the natural base e, which we call Euler's number, or the natural base. And so we want to investigate what this is really quickly. So if you'd like to take a minute, I'll pause it. And what I'd like you to do is try to fill out this chart. Okay, so we have this guy over here. I'll use my pointer if I can find it real quick. There it is. So we have this equation here. 1 plus 1 over n, all raised to the n. And then what your n are these numbers here. So to get 2.594, we put in 10. So we have 10 squared, which is 100, 10 cubed, which is 1,000, then 10,000, 100,000, and a million. Okay? And so each time you're plugging in a different number and seeing what comes out here. And what you should see is a slight pattern headed towards a certain number. So I'll give you a minute to go ahead and do that. Okay, hopefully you paused it and you went through that little thing and you see that as we are solving this all the way through, what we're coming to is that we get to a place where E is roughly about 2.718. Alright? So as you plug these in, your number should be getting closer and closer to 2.718. I believe it's 2.8 at the end here. Okay? And the reason we do this is just to show that basically E is just a number, similar to pi, I, different things that we use in math to represent certain numbers throughout. Okay? And so all we're doing is just working with the natural base today, and our goal is to just do all the things that we've been doing with all the other exponential growth and decay from 7.1 and 7.2, but now we have a specific base in mind. And what happens is this number E continually shows up in nature, in patterns in the rings of trees, and different patterns throughout nature that that grow exponentially. And they seem to all have a base of E, which was discovered by Euler, and which is why we call it the natural base. And then we gave it the term E for his name Euler. Okay? Alright. So in our first example here, we're just working with the base E, and it's really about showing that nothing is changing in our rules. So we have a base E to the third times E to the fourth, so what we really have is E to the 3 plus 4. Because when the bases match, and you have two different exponents, you add the exponents. Even if they're the same exponents, you would still add. So you end up with E to the 7th. Right? B here, we have 10E to the third over 5E squared. So what we have is 2E to the 3 minus 2, or just 2E to the first. Okay? And then over here we end up with 3 to the first, E to the negative 4x, all squared. So 3 to the first squared becomes 9, and then E to the negative 4x becomes E to the negative 8x, because you multiply exponents when you have an exponent raised to an exponent. Okay? Continuing on, we want to evaluate this expression with our calculator. So we're going to get our calculator. And to evaluate on your calculator here for E squared, we're going to start with the button second. Okay, and then ln, which would give us, right above it, is E to the x. Alright, so that's in blue. And what your screen will show, it'll look like this. It'll say E to the, and then whatever. So right now we want to raise to the 2 and close parentheses and then hit enter. And that should equal 7.389, or round it to 7.39. So that's A. In our other one we want E to the negative 0.06 and then enter. So E second ln negative 0.06, enter, I get 0.942. Okay? And again, when we have a negative exponent, it's really 1 over E to the 0.06. Alright? So that lets us evaluate negative exponents, positive exponents, any exponent above e. Alright, so we're going to graph with the natural base, and if it has a positive exponent, like we have here with positive 0.75x, then we say it's growth. Alright, so the first thing I want to do is I want to create my x and y chart. Ooh, that was an ugly chart there, sorry. So I'll do that, x, y. Alright, and then we plug in what we've got there, 2e to the 0.75x. Alright, so 0, 1, 2, e to the 0.75 times 0. Alright, so then we end up with 0.75 times 0 is 0, so e to the 0 is 1. So 1 times 2 is 2. Alright, then we get 2 times e to the 0.75 times 1. So e to the 0.75, this is where we get our calculator out. Second ln to the 0.75. And then I multiply that by 2, and I get 4.23. Alright, so on our graph here, at 0, we're up, let me mark out the dashes. So at 0 we're at 2, and at 1 we're at 4.23. And again, this is growth, so it's going to come from the x-axis and shoot straight up. Our asymptote is right here, still at y equals 0. There is no h and k, so we have no shift, so we have our final graph. And I would label my points. 0, 2, and 1, 4.23. Okay? Alright. Okay guys, so we're going to do a more complicated version of graphing. What you can see here is I have y equals e to the negative 0.5 times the quantity of x minus 2 plus 1. So one more time with gusto. We have y equals e to the negative 0.5 times the quantity of x minus 2 plus 1. So I have an h, I have a k, I have no a, so that means a is 1, and my base is e, but I have a negative out in front here, which makes this a decay problem. So I write a little note, decay. Alright, and again we want to create our XY chart, and we get e to the negative 0.5 x. So this is our OG, because what I'm doing is I'm writing the graph without my h and k. So I'm going to circle my h and k so that you can see I'm writing my equation without that part of it, because we need to graph that part first, our OG, and then shift our OG, our original graph. So again, at 0, we end up with e to the 0, e to the negative 0.5 times 0, which makes 1. And then at 1, we end up with e to the negative 0.5 times 1. So what I have is second ln negative 0.5. Enter. And I get 0.61. Okay? So again, these ones you want to make maybe your spacing on your graph a little larger so that you have room to work. So I'm going to every other one on my graph paper here. Okay? So for 0 I've got 1, and for 1 I have 0.61, which is a little higher than 0.5. Okay, and I know it's decay, so I know it's going to come down like this, swoop, and get really close to the asymptote. And again, our asymptote here, our asymptote here is going to be right along the x-axis for y equals 0. So this is our original graph, and we need to shift it. We need to shift it according to h and k, and again, from our equation up there, h is 2 and k equals 1. And that comes from this area here. H is 2 and k is 1. And so what that means is I'm going to shift to the right 2 and up 1. And so I'm going to do my final graph here in blue. And so I'm going to go over 1, 2, and up 1, and mark my point. Then I take this guy and I go over 1, 2, and I mark my point. And I need to go up 1, excuse me, right there. And then I have a new asymptote that's going to be at 1. So my asymptote will be here in blue. Y equals 1, because it matches my k, just like our 7.1 stuff. So our graph will come up, should hit both points, and then shoot right along the asymptote, because it never touches 1. Okay, so domain. Domain for this, again, is all real. And range would be y greater than 1, because it can't be 1 and it can't be below 1. So as we see, our graph is right here. It's swooping down, getting really close to 1, but it's never going to be down here for y values that are below 1. Okay? So again, we took our original point, we shifted it over 1, 2, and up 1. Then we took this guy and we shifted it over 1, 2, and up 1. Okay? Here we just have some problems to practice with. I would use these to add on to any of the practice that you're going to have to study for our test. We can go over a couple of these later. All right? Thanks.